Hi, this video is about choosing which method we are going to use to find the antiderivative of a function. Our common rules are power and u substitution, but there are other rules as well. One of these options was even before we talked about what antiderivatives were. By just looking at the sign of the derivative, we can tell what is going on with that original function. So in both a and b, we didn't actually even need to find what the antiderivative was. We can just look at the sign of that derivative in order to make determinations about what is going on with our original function. So neither of these did I even need power rule or u substitution. If, however, we're actually asked to find a population function, okay, now it is time to find my antiderivative of this function. This is one where we can just use our power rule, where we can just add 1 to our exponent and then divide by our new exponent in order to get this population function sort of set up. We are doing an indefinite integral, so it needed this c. And then in order to figure out what that c value was, we needed to use this initial value that we were given, that initial population of 1,000. So plugging that into our function, we figure out what our c value is, being 8,000. And then we can plug that into our population function. To estimate the population after 10 years, that's just a matter of plugging in that 10, but that's not a focus of our video. Mostly we're just checking what method do we need here, and it just turned out to be power rule. One of our indications that we need to do u substitution, which is needed in this one, is if we start seeing multiple pieces being mixed together. So there is inner and outer functions. We have this outer function of this with our x squared minus 9 inside. And we also have this additional thing. If we wanted to do power rule on this problem, we would have to FOIL out that cube and then multiply by that 2x. I don't want to do that because we can just kind of say, hey, this is sort of our innermost thing. So our u is going to be x squared minus 9. So our du over dx is going to be 2x, making du equal to just 2x dx. But then, hey, we're like, oh, cool. That thing is sort of showing up right there. So our u substitution actually works pretty well. After that point, we can start subbing in our things. So this is our u. So now we have a u cubed, and we can replace this 2x dx with just a du. So this equals u to the fourth over u over 4 plus our c, because we have an indefinite integral, and then it's just a matter of plugging back in that x squared minus 9, keeping everything else the same as what it was. So we get x squared minus 9 to the fourth over 4 plus c. I can't figure out what that c value is because this problem did not give me an initial value. In this definite integral problem, I can't use my power rule because there are no exponents. I can't do u substitution because there's nothing really to sub out with that u. I could find the derivative of sine, that's cosine, nothing really to sub around. So instead I need to think about, okay, well, what do I know about derivatives in order to figure out whose derivative is going to be sine? I know that the derivative of sine x is cosine, so if I do the derivative of cosine, which is very similar to what we have right here, but it doesn't have that negative there. So if we just slap a negative on this thing, we are going to be okay, because the derivative of negative cosine would be a positive sine. So this thing is going to equal negative cosine x on the interval from 0 to pi. And now it's just a matter of doing top minus bottom. So we do negative cosine of pi minus negative cosine of the bottom, 0. The cosine of pi is just negative 1, plus the cosine of 0 is 1. So we get 1 plus 1. Oh, so this just equals 2. So sine x dx just equals 2. All set. This problem is an example of power rule not working, u substitution not working, and we don't have a nice thing whose derivative is a base to some x exponent. Instead, we have this special rule in order to figure out what the antiderivative of this function is. Since this is a definite integral, we're just not going to have to worry about that plus c part. We can just do that 1 over ln of a, which is 1 over the ln of 3 multiplied by 3 to the x, going on the interval from 2 to -1. And then we could just plug in our values doing the fundamental theorem of calculus. We get 1 over the ln of 3 times 3 to the -1 minus what we got on our bottom, which is 1 over the ln of 3 times 3 squared. So if we clean this up a little bit, we don't really need to, but I'm gonna. So we get 1 over 3 ln of 3 minus 9 over ln of 3. And I'm feeling sassy, so I'm going to simplify this a little bit more. I'm going to make this common denominator here, so we get 27 over 3 ln of 3, which equals negative 26 over 3 ln of 3. Like, that's super simplified. I could have stopped way back in the red and pink spot. I didn't. So I did it because I'm feeling sassy. This is just one of those rules that we need to have memorized in order to be able to do problems like this. This problem is an example where it's not immediately clear what I should be doing in order to find this antiderivative. So I'm going to play with it a little bit. So we could make this instead the antiderivative from 1 to 8. I'm going to make that a square root of 2 over the square root of x. And then I'm like, oh, well, could I do something more in order to be able to really identify what that power is? Because it might be an ln thing, but I'm not sure yet. So what if I did the antiderivative from 1 to 8 of square root of 2? Could I get that x out of the denominator nicely? Well, I could make it an x to the -1/2 dx. And if I apply my power rule to that, am I going to end up with some sort of x to the 0? Well, no, if I add 1 to that, I'll get positive 1/2. So I should be able to find this thing a-okay. So this becomes the square root of 2 x to the positive 1/2 over 1/2 on the interval from 1 to 8. Just to make my solving a little bit simpler, I'm just going to rewrite this as 2 square roots of 2 x to the 1/2 on the interval from 1 to 8. And now I just need to do top minus bottom. So that's 2 square roots of 2 times the square root of 8 minus 2 square roots of 2 times the square root of 1. Well, hey, the square root of 2 times the square root of 8 is the square root of 16, and the square root of 16 is 4, so this is 2 times 4. Minus 2 square roots of 2. All done. Again, I didn't need to fully simplify that thing, but I did. Why not? Working on this example, I would start by thinking about power rule. No way. Instead, think about that u substitution. So u could be secant squared theta. But if I try to do the derivative of that, so du is going to be 2 secant theta multiplied by the derivative of the inside, which is secant tangent. And that's not really working very well because I can't get another secant squared if I do that u squared. So it can't be that. So otherwise my u would be tangent squared theta plus 1. I try that. That doesn't work either. I get du equals 2 tan theta times secant squared theta, and that's still not substituting in right. So I got to think about something else. What I do remember is there's something about Pythagorean identities. Way back in the day, we talked about how secant squared theta equals tangent squared theta plus 1. Since those things are equivalent, we can replace this denominator with secant squared, which rewrites our definite integral 0 to pi over 4 as secant squared theta over another secant squared theta d theta. But hey, that is just the antiderivative from 0 to pi over 4 of 1 d theta. Oh, well, that's easy now. That's just gonna be theta going from 0 to pi over 4. Okay, cool. The big trick about this problem is being able to spot that. Being able to spot that we have a Pythagorean identity in this problem. The only Pythagorean the only trig identities that we need to be dealing with in AB calculus is the Pythagorean ones and the reciprocals. We won't need to do double, half, or whatever. That is in BC calculus. But for our purposes in AB, it's just the Pythagorean. In this example, I'm really feeling like u substitution, but it gets a little bit weird when I try to apply it. I feel like that's the innermost function, so I want u to be 4x cubed minus 9, making du into 12x squared dx, which doesn't quite match the piece that I'm left with. The thing I want it to match with is this 6x dx. Well, really, it's just half off. If I just do a little bit of a discount on here and divide both sides by 2, I could still substitute in. So don't be discouraged if your u substitution doesn't match right away. See if there's a little bit of manipulation you can do with that what du equals in order to be able to still substitute it in. Because now we're able to substitute in so that we get, and then our 6x squared dx gets replaced with a du and a 1/2. I'm going to choose to put that in front because then it's just going to make my integration a little bit simpler. I still need to have this to be a 1 over u cubed. So this is 1/2 the antiderivative of u to the negative 3 du, which equals 1/2 u to the negative 2 over negative 2 plus c, which equals negative 1/4 u squared plus c. Now I just got to sub that u back in. So this is negative 1 over 4. I've already forgotten. 4x cubed plus 9 minus 9 squared plus c. So if your u substitution doesn't match right away, see if there's small bits of manipulation you can do so it matches up nicely. And if it doesn't, start looking at other methods. That's the end of our video on choosing methods for anti-differentiation. So the ones we talked about is number 1 is just try to get that power rule going. If that's not working, do some u substitution with maybe additional bits of manipulation. If that's still not working, then double check, are there some weird rules that we have, weird ideas that we know about antiderivatives versus derivatives in order to figure out what our antiderivative is? And if you're still having trouble, it's only then that you start thinking about, are there trig identities that we can use, particularly the Pythagorean identities? Thanks for watching. Bye-bye.